In traditional clinical trials, we encounter a specific statistical paradox. Surviving a disease longer than someone else does not guarantee that the mathematical models will record your outcome as a victory. For decades, the gold standard for evaluating patient outcomes has been the time to first event analysis, powered by the Cox proportional hazards model. Consider two patients. Patient A suffers a minor, easily treated hospitalization at month 6, but survives for 5 full years. Patient B experiences 0 hospitalizations, but dies abruptly at month 20. When the Cox model scans this data chronologically, it stops tracking patient A at the exact moment they enter the hospital at month 6. It logs their hospitalization as the first event, and formally excludes their subsequent 4.5 years of survival from the primary efficacy analysis. By utilizing the first event to trigger the endpoint, the mathematics treat every component of a composite outcome with identical severity. Equating an easily managed hospital visit with cardiovascular death based entirely on chronological order strips away the lived reality of the patient. The model records the timing of the failure, but neglects the gravity of the outcome. To bypass the limitations of time-to-first event models, biostatisticians led by Stuart Pocock introduced a non-parametric alternative, the win ratio. The core operational mechanism of the win ratio is a massive pairwise comparison matrix. The algorithm takes every single patient in the experimental treatment arm and mathematically matches them against every single patient in the control arm, generating thousands of unique pairs. Each pair is then evaluated through a strict lexicographic hierarchy. The algorithm evaluates terminal events like mortality first. If that results in a tie, the comparison descends to the second tier, evaluating severe morbidity like hospitalizations, and then down to quality of life scores, stopping the moment a winner is identified. The logic appears elegant on paper. It prioritizes death over discomfort. However, exposing the standard unadjusted win ratio to the messy realities of real-world clinical data reveals 3 specific mathematical blind spots. To build an algorithm that accurately measures human suffering, we must stress test the win ratio against 3 distinct pressures: unmeasured toxicity, patient preferences, and recurrent disease. The standard clinical hierarchy operates on a rigid assumption defined entirely by physicians. Overall survival is the absolute priority, regardless of how brief the extension. Empirical preference data from patients in oncology and neurology contradicts this assumption. Patients consistently rank severe, debilitating drug toxicity or permanent physical disability as a worse outcome than a marginal extension of life. We see this disconnect clearly in the historical NCIC CTG PA.3 trial, which evaluated the targeted therapy erlotinib for advanced pancreatic cancer. Under conventional metrics, the drug demonstrated a statistically significant survival benefit and was deemed a success. This diagram compares algorithmic routing logic. Re-evaluating the trial data using the patient-elicited hierarchy on the right, we apply a clinical efficacy margin. To score a win on the primary survival node, the drug must extend life by strictly more than 2 months. Because the actual life extensions provided by erlotinib were negligible, the vast majority of patient pairs fail to clear that 2-month threshold. The algorithm is forced to declare a tie on survival and cascades down to the secondary tier, severe toxicity. This routing change alters the drug's apparent efficacy. Erlotinib carried a 90% rate of severe treatment-related adverse events. When evaluated on the toxicity node, it overwhelmingly loses the pairwise comparisons against the placebo. This graph maps the resulting impact on the net benefit statistic. Without the threshold, erlotinib shows a 2.3% positive benefit. By implementing the patient-mandated 2-month minimum, the mathematical outcomes flip, revealing a negative 3.6% net benefit. If we fail to integrate patient-elicited thresholds into the matrix, the algorithm forces therapies to succeed mathematically while failing the patient clinically. The second vulnerability in the win ratio arises from informative censoring. This occurs when patients suffering from severe drug toxicity withdraw from the trial, effectively erasing their subsequent medical trajectory from the database. The win ratio operates under a strict minimum follow-up rule. It can only compare a patient pair across a shared window of time. If an experimental patient drops out at month 3 due to side effects, the comparison window shuts at 90 days. Because the algorithm is locked to this truncated window, it becomes completely blinded to the future. If that same treatment patient dies from disease progression at month 8, the algorithm ignores the fatality. This creates the toxic success paradox. Because the death is unobserved, the algorithm calls a tie on mortality. It drops to the lower tiers, evaluates early symptom improvements recorded before the month 3 dropout, and awards the win to a toxic drug based entirely on transient relief. To prevent toxicity from masking mortality, statisticians utilize a mathematical rescue mechanism, inverse probability of censoring weighting, or IPCW. IPCW utilizes survival modeling to calculate the exact probability of a patient remaining uncensored at any given point in the trial. It then re-weights the patient pairs who successfully stayed in the study by the inverse of that probability. By applying a mathematical multiplier to rare, late-surviving patients, IPCW turns them into statistical proxies. They mathematically substitute for the patients who were lost to toxicity, restoring balance to the risk set. This chart visualizes the vulnerability of the raw algorithm. Under conditions of zero censoring, the true treatment effect sits at 55.5%. As toxicity dropouts scale up to 44%, the unadjusted gray bars collapse, pulling the win proportion down to 31%. When the IPCW correction is applied to the exact same datasets, the dynamic reweighting neutralizes the missing data. The blue adjusted bars remain perfectly anchored at the true 55.5% baseline. If trial designers do not actively correct for informative censoring, the raw mathematics will effectively reward experimental therapies for poisoning patients early. The final vulnerability of the win ratio is its erasure of cumulative disease burden. Chronic progressive illnesses are defined by repeated physiological impacts that eventually culminate in cardiovascular death. Patients routinely experience multiple non-fatal hospitalizations, ER visits, and outpatient interventions before a terminal event. This cycle generates a massive volume of clinical data reflecting the true progression of the disease. The established approach for capturing this volume is the Anderson-Gill model. Unlike older methods, Anderson-Gill keeps the patient in the continuous risk set. It actively counts the second, third, and fourth hospitalizations, measuring the aggregate burden the patient sustains over time. When evaluating the win ratio on its secondary morbidity tier, we find a specific structural limitation. It ignores recurrent events entirely, discarding everything after the very first hospitalization. This diagram maps a single patient journey across 3 analytical frameworks. The patient experiences hospitalizations at 6 and 15 months, and a terminal event at 21 months. The red time to first event line triggers at 6 months and stops permanently. The blue Anderson-Gill line continues through the timeline, capturing all 3 distinct event notes. The purple win ratio line drops its anchor exclusively on the cardiovascular death node, ghosting through the recurrent hospitalizations, leaving the intermediate suffering unquantified. This creates a severe clinical paradox. Imagine patient A has 5 hospitalizations, while patient B has only 1. The standard win ratio awards patient A the win, provided patient B's single hospital visit happens slightly earlier in the calendar. To solve this, methodologists developed the last event-assisted win ratio. This upgrade introduces a dual logic system to the secondary tier. If a pair ties on mortality, the algorithm first counts the total cumulative frequency of events. The patient with fewer hospitalizations wins. If their frequencies are identical, it breaks the tie by prioritizing the patient whose latest event occurred furthest into the trial, rewarding therapies that delay disease progression. Combining the data capture of the Anderson-Gill model with the hierarchical logic of the win ratio is the only mathematical way to accurately reflect the progressive trauma of chronic disease. The win ratio provides a necessary alternative to the time to first event framework, but the raw algorithm remains vulnerable to data distortion. To secure the model, we must implement 3 precise upgrades. First, we must hard-code patient-elicited efficacy thresholds into the hierarchy, ensuring that a mathematical win reflects a meaningful quality of life improvement. Second, we deploy IPCW to aggressively correct for informative censoring, preventing unrecorded toxicity dropouts from hiding fatal outcomes. Third, we integrate last event-assisted logic into the lower tiers to capture the total cumulative burden of recurrent morbidity. For global regulatory bodies like the FDA and the EMA, these adjustments are no longer academic theory. They are becoming the strict requirements for proving true clinical benefit. By calibrating our biostatistics to the physical realities of the disease, we ensure that trial results reflect the patient's actual clinical trajectory.